All right. So
okay, well, it's a weird conversion of my PDF to PowerPoint, but anyway. So my name is Emmanuel Marcq. I work in the Latmos laboratory in Guyancourt, France, and I will address a short review of the measurements of sulfur dioxide, which we already have heard about in the two previous talks, both above and below the clouds of Venus, and how they can help us in preparing the next generation of instruments designed to measure them. So next slide, please.
oh, okay, sorry.
Okay, so it was already addressed by the previous speakers, in particular Frank Mills, but SO2 is involved in a lot of processes in the atmosphere of Venus, both related to the cloud formation, since SO2 is a precursor species through photooxidization of the sulfuric acid clouds that we can see. It may be also involved in the UV absorber chemistry if it's a sulfur-bearing species, which we are suspecting, even though we have no confirmation of that. Below the clouds, we also expect the long-term source for SO2 if we want to avoid a long-term depletion by surface sinks. So on a time scale of 10 million years to be volcanic outgassing. So it's a species that can also be used to assess the coupling between the interior and the atmosphere. And since SO2 has a very different and a much shorter lifetime above the clouds compared to below the clouds, the observation of the variability of SO2 above the clouds is a very good tracer of general circulation patterns at cloud top level, and also the vertical mixing between the source, the short-term source of SO2 below the clouds, and where it's quickly destroyed in a matter of hours and days above the clouds. So next slide, please. So actually, the recent measurements I will talk about for time constraints will only be mine. I know that other observers have observed Venus recently, but I will focus on the observations I've been involved with. So next slide, please. The first one, above the clouds, I've been mainly involved in measuring SO2 using the SPICAV instruments on board Venus Express. So the most recent paper was published in 2020 in ICARES for the reanalysis of the whole datasets spanning from 2006 to 2014, where he have on a time scale, on typical time scale of a few months, 2 to 3 orders of magnitude variability, with times where SO2 is very abundant, and then lows at least 2 or 3 orders of magnitude below these maxima. We are in quite good agreement also with the measurements from HST, shown in diamonds here, and done by Candice Lea-Gisep. So the overall trend is decreasing, but you see that you can have, even during a time of decrease, small short increases of SO2 that can be visible. How can we measure that? It's shown on the left side figure. We observe the reflectivity in the UV range of the Venusian atmosphere, and the fact that SO2 is absorbing near 220 nanometers and also near 280 nanometers. So the appearance of these two absorption bands is a good way to measure SO2 with an accuracy that is satisfying here, at least better than 50% in general. Okay, next slide, please. Just on 2 figures. So the left on figure was shown by Franklin Mills, and show the latitudinal pattern of SO2 variation, where it's more abundant close to the equator and with a large variability in the lower latitudes, and a globally smaller mixing ratio for SO2 at higher latitudes, and also far less extensive dispersion of measurements. Dispersion is very high at low latitudes. It's consistent with the pattern that was seen by other observers, namely the plumes of SO2 that only occur at low latitudes close to the equator, that can give a transient, very strong transient enhancements in SO2, but restricted to the lower latitudes. And then SO2 is slowly advected by the Hadley circulation to the higher latitudes, where it's depleted during its transport, which yields a smaller variability and smaller average values. The sensitivity also of SO2 with respect to to photochemistry can be also shown through the dependency at low latitude with respect to the local solar time, where we definitely have a lower mixing ratio occurring close to the subsolar point, where the photochemical destruction is probably enhanced, occurs at an enhanced rate. So next slide, please. Now, below the clouds, we can observe also SO2, but this time on the night side using the thermal infrared radiation coming from the deep atmosphere, and that goes through layers below the clouds close to the 30 to 40 kilometer altitude range, where we have absorption by various minor species, including sulfur dioxide. And its spectral signature is actually restricted to a very narrow band. You see, it's the gray area here, close to 2.46 micron, and where, thanks to the very high spatial resolution of iShell at IRTF, close to 20,000, we were able to really distinguish the SO2 lines from the neighboring OCS lines that occur in this kind of spectrum, and doing that in several locations on the Venusian disk. We have here a pattern of increase with increasing latitude, with a minimum that is slightly shifted to the southern hemisphere between -20 and 0 degree in latitude, with average values slightly higher than the commonly accepted values. The common range is 140 ppm plus or minus 50 below the clouds. That is the value derived from the observation performed in the 1990s. And here we're closer to 180 ppm. So still compatible, but slightly higher compared to previous estimate. And next slide, please. So we also, in the light of these measurements, we wanted also to see if we could measure SO2 with the whole archive of the Vertis Edge dataset. So starting in the same line, but at a spectral resolution about 10 times lower compared to the previous spectra. So you see basically the same spectra, but with a far worse spectral resolution. And here the SO2 signature is only limited in a single bump just at the end of the spectrum to the longer wavelengths. And so processing lots of spectra, because that's the advantage of space mission. We have large data sets. We can derive average value that are compatible with the average value that we had with iShell. We are hovering about 200 ppmv at 35 kilometer, but the accuracy of these measurements is quite poor due to the low spectral resolution. And so we are not able to confirm nor deny the value derived from iShell. So the previous data points are shown in diamonds here. And so we remain within the envelope of the possible range of SO2 that we retrieve with Vertis Edge. So that gives an important clue for us that to derive accurate SO2 mixing ratio below the clouds, you need a very high spectral resolution. We can already say that. So next slide, please. So now mentioning the future measurements that can be performed with Envision. So I would say the spiritual successor of Vertis H is named Venspec H, and so we also so build on this Vertis H heritage by improving the spectral resolution by a factor of 4, which should allow for measurements of SO2 in the so-called band 2, which is the same band that we observed here with Vertis H and iShell. And under the clouds should read an accuracy on SO2 at about 30%. And in a reflected component, where the absorption of SO2 can also be seen, an accuracy of about 20% is expected. So next slide, please. Now for the successor of SPICAV UV, which is named Venspec Q. It's a UV spectrometer that will observe the same spectral region with a broad, low-resolution channel comparable to SPICAV UV, but encompassing until the maximum absorption of the UV absorber in order to study simultaneously the UV absorber and the sulfur gases, and a narrow channel with a higher spectral resolution, which is designed to separate the individual lines of absorption of sulfur dioxide compared to sulfur monoxide. Both gases are degenerate at lower spectral resolution, but at a higher spectral resolution, we can separate both. And we aim for a 15% accuracy, so an improvement of about a factor of 2 to 3 compared to SPICAV UV. And next slide, please. And the third way that Envision will be able to measure the sulfate gases will be using the radio science experiment. So using the refracted and absorbed the reflection and the absorption of the data link between the Envision probe and the ground station on Earth, we can separate the parts since we use two different bands, so in X band and Ka band. It's possible to separate what is due to absorption from what is due to refraction. And in such a way, the absorption of sulfate species, among them gaseous sulfur dioxide, can be measured in the 45-50 kilometer altitude range, which is highly precious, I would say, because that's the altitude range that is otherwise cannot be accessed except from in situ measurements, because it's too deep in the clouds to be seen in UV and too high in the atmosphere to be seen in the thermal infrared. So that's a sort of gap in the measurements that can be filled only in this way for remote observations. And so we can go to the last slide, I guess. Yes, the conclusion. So SO2 is arguably and most likely the most variable trace species in the whole Venus atmosphere, spanning 2 to 3 orders of magnitude, both in time and location, according to time and location on Venus atmosphere. So concerning its variation gives very precious insights on small scale and large scale dynamics and chemistry also, and gives also lots of insight about the process reading the clouds, the surface atmosphere interaction, the coupling between carbon, water, and sulfur cycle in the chemistry of the atmosphere of Venus. And one would like that the Envision project will be probably the first mission able to monitor SO2 both below, within, and above the clouds, so in 3 different regions with a large spatial and temporal coverage, and so could probably teach us a lot about sulfur chemistry in this atmosphere once it will fly. And I thank you for your attention.